Hello and welcome to our video about Kepler's laws of planetary motion. In this video, I will explain everything you need to know about these laws. Johannes Kepler, a renowned 17th century mathematician and astronomer, discovered these laws while working with the data of Tycho Brahe. His laws explain how planets move around the Sun, forming the fundamental basis of planetary motion that we know today. The first of Kepler's laws, also known as the law of ellipses, states that planets move in elliptical orbits with the Sun at one of the two foci. To better understand, let's clarify what an ellipse is. An ellipse is a curved shape that looks like a flattened circle. It's defined by 2 points called foci, the plural of focus, such that the sum of the distances from any point on the ellipse to the two foci is a constant. In terms of planetary motion, this means that the path each planet follows around the Sun is an elliptical shape, and not a perfect circle as had been previously believed. The Sun isn't situated at the center of this ellipse, but is instead at one of the foci. The closest approach of a planet to the Sun is called perihelion, and the farthest point is called aphelion. The line joining these 2 points is the major axis of the ellipse. The point exactly halfway between the perihelion and aphelion, which would be the center in a circular orbit, is known as the semi-major axis. The first law upended the long-standing belief that heavenly bodies moved in perfect circles. This shift in thinking was a critical step in our ability to more accurately model and predict planetary motion. The second of Kepler's laws is often referred to as the law of equal areas. This law states that the line that connects a planet to the Sun sweeps out equal areas in equal times. So, what does this mean exactly? Imagine a line drawn from the center of the Sun to the center of a planet. As the planet moves along its orbit, that line will sweep out an area between the planet and the Sun. Kepler's second law says that in equal periods of time, that line will sweep out equal areas. This has an important consequence for the planet's speed. When the planet is close to the Sun, it moves more quickly, allowing it to sweep out a larger portion of its orbit. But because it's closer to the Sun, this large sweep of the orbit only covers a relatively small area. On the other hand, when the planet is farther from the Sun, it moves more slowly, covering a smaller sweep of its orbit. But this smaller sweep covers a larger area, because it's farther from the Sun. So, in both cases, close to the Sun and far away from the Sun, the planet sweeps out the same area in the same amount of time, meaning it moves faster when it's closer to the Sun and slower when it's farther away. This concept is known as conservation of angular momentum. An example of this would be Earth's orbit around the Sun. In January, Earth is closest to the Sun at a point called perihelion, and moves more quickly. In July, Earth is farthest from the Sun at a point called aphelion, and moves more slowly. The third of Kepler's laws, also known as the law of harmonies, links the orbital period and radius of orbit of a planet to the Sun. This law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This might sound a bit complicated, so let's break it down. The orbital period is the time it takes for a planet to complete one full orbit around the Sun. The semi-major axis is essentially the average distance from the planet to the Sun over the course of one orbit. So, if we know how long it takes for a planet to orbit the Sun, we can find out the average distance of the planet from the Sun, and vice versa. This relationship holds true for all the planets in our solar system. For example, Earth's orbital period is 1 year, and its semi-major axis, or average distance to the Sun, is 1 astronomical unit, or AU. If we take a planet like Mars, its orbital period is about 1.88 Earth years. If we square that, 1.88/2, we get approximately 3.53. The cube of Mars's average distance from the Sun is 1.52/3, which also yields approximately 3.53. This law allows astronomers to calculate distances in our solar system and beyond, providing a vital tool for understanding the universe. And that's it for today. Stay curious, keep asking questions, and continue exploring the wonderful universe we live in. Thank you for watching. Please remember to give this video a thumbs up, subscribe to the channel, and leave a comment. Let us know what other scientific principles you'd like us to tackle next. Until next time, keep looking up.